Hi.
All right.
Go.
Hi. I remember having quite a lot of fun when I was young playing video games, but now that I have 6 kids, I see how easier it is to access a video game anytime, anywhere, and how time-consuming it can get. This is part of why at Frima we decided to create a branch called Frima Lab, whose goal is to bring back physical play while conserving the best aspect of what video games are. Today the talk is going to be about smart toys or connected toys and how to go from design to prototype and all of the steps to get there. The talk is pretty high level, but in many different areas of expertise, so please bear with us. I'm Jean-Philippe Auclair, and I've been working at Frima for the last 7 years. I started as a MMO engine developer, then a 3D Flash engine developer, then I switched to Unity, and now I'm having pretty much the most awesome job.
I'm Simon. In the last years, been working in our 2D game engine. And in the last 2 years, I make smart toys with my partner, JP.
Right. So smart toys or connected toys, basically any physical toys that communicate and interact with the video games, either on the consoles or mobile. For us, it started in 2011 with Skylanders. We've worked on the MMO, web-based MMO of Skylanders, and we had to create some kind of driver to communicate with the physical portal of Skylanders. And on the market, there was multiple different projects since then. Think about Anki, Disney Playmation, Sphero, BB, and a lot. Every month now, there's a lot of new projects going out. And but we're not here to talk about what the others did. We're here to talk about our stuff. And today in this session, we're going to follow 2 of the prototypes we've made. The first one is a 40-play workbench, and the second one is 40-play racer. And I'm just going to start with a video showing what they are. So what we see here is workbench, classical workbench, so everybody know what it is. And it communicates wirelessly with iPad. So you have a couple of plastic tools and a platform that we prototyped, which includes sensors. I'll just let it go so you can check it out. And the second game here is a classical racing game on the iPad. But this time, instead of using a virtual controller on the iPad or any kind of gamepad, we actually shrink down the electronics to fit inside the die-cast car. So the kids are controlling their vehicles using the cars. So it's pretty magical. And we have a shot of the Unity game here that we've prototyped for this same thing. So you see the car going around in the air. We track the orientation of the car in any axis, so we can do some kind of jump and super special tricks. All right. For most prototypes, we start with a brainstorm. In this case, in the case of the workshop, it was pretty easy. Strong emotional bound. Everybody know what it is. Everybody played with that, and we know the exact target audience and who's interested with it. And there was a big opportunity since there aren't any kind of interactive toys in this space right now, and it was easy to pick as one of the prototypes to do. For any smart toys that we do, we have to think about 2 sides. So there's always the physical size and the digital size. And we always use Unity for all the prototypes, and we are going to come back on that later. And for the game itself, well, we have a target audience very, very young. So we had to go with something very simple, such as a diner dash kind of game where you complete a couple of steps to clear out the objectives. As for the physical part, we had to construct something very robust that kid wouldn't be able to break, and choose a couple of inputs and tools that the kids already know, so hammer and screwdriver and that kind of thing, plus a platform that would be able to record any kind of interaction that the kids were doing. For the next few slides, we are going to talk about electronics and since it's part of the first steps inside of the development of a smart toy. So please bear with us. When you choose a sensor, there are multiple options, a lot of different kind of sensors, different quality, and you really gotta take what you need, only what you need. In this case, the workbench, we have a hammer. We could use a button under the nail on the platform, very simple. For the saw, it was a bit more complex, but we had to print some kind of 3D plastic part to handle every tooth of the saw to hit against. So there, again, it's a simple button underneath. And then there is a rotary encoder for the screwdriver and the wrench. So we have very precise input in both directions. And for the ruler, there is an optical higher distance sensor. What you must have is always the datasheet. If you go and find a good sensor, a good component, and you go online to buy it, make sure you have the datasheet. If you don't, you're going to buy the thing, you will receive the component, and may be totally unable to use it because, well, there's no documentation at all on it. So first step, before buying anything, make sure you have the datasheets. And don't go crazy over whatever component you're choosing. For instance, in one of the projects we did, there was a spotlight, and we started with a 1-watt LED, and then we saw online a 3-watt LED, and then we saw a 10-watt LED. So we were like, yeah, it's going to be awesome, 10-watt LED. So we bought the thing, we received it, assembled it on the 3D printed spotlight, and started it. Then it burned the thing, dripped, melted, everything was destroyed. So take only what you need, not more and not less.
All right. So you have all those sensors, but these little guys, they don't work alone. They need some kind of bus that can communicate with them and configure them, and it's a microcontroller. If you're new to electronics, what we suggest is you go to eBay and try to find a package that includes an Arduino and a bunch of sensors. This way, after playing with a couple of projects, you will be able to understand most of the topics in electronics, and that way you can select the right microcontroller for your next idea. After you found the microcontroller that you like, what we suggest is you try to stick with it and stop looking around, because you will always find a model that have more power, more options, and you will spend all your time porting your code over and over. So what we did in our case is to select two models. We have one for low power and low CPU application, and we have another one if we have CPU intensive, or if we are using high-speed peripherals, such as an LCD, an SD card, or if the project requires USB functionality, for example. So you have all those components, you will need to buy them. One of the choices is to go through an online distributor, such as DigiKey. These guys are very convenient because they offer next-day delivery, but they are a little bit costly, though. If you're in the middle of a project, that's probably your best choice, because you simply log into their website, you order the parts, and the next day you're good to go. So that's very good. However, if you have a little bit of time ahead of you, there's two stores that we like a lot, which are eBay and AliExpress, especially those sellers in Shenzhen, China. They have very low price, they have a lot of components, the quality is surprisingly good, but you will get slower shipping. Let's say a couple of weeks to receive your product. Sure, you can pay for extra shipping if it makes sense. So the components are harder, you can start your electronic design. You should start with a dev kit. Those are inexpensive for most microcontrollers. Very easy to use. You simply receive a box. There's a USB cables connected to your PC. You go to the manufacturer website, and then you will get a software package that includes the software with the samples related to your dev kit. So for example, if you buy a Bluetooth dev kit, you will have samples such as BLE beacons and heart rate profiler, for example. So you simply open the project, you press on play, and you already have something that runs on your mobile device. Also, the dev kit exposes all the pins, so it's very practical and will adapt to any of your future idea. Some of the dev kit are also able to upload new firmware to external boards. So it's very convenient because it will save you the cost of buying extra hardware tools. But the dev kit have limitation with smaller design. Imagine we would take this dev kit with the racer toy you saw at the beginning. That would give the burger Arduino. So as you can see in the picture, it doesn't fit very well. So the dev kit is good at the beginning of a project. It's very good for debugging. It might work for a bigger toy, but if you work with small design, there's a better choice. And that is to learn how to make your own PCB which are printed circuit board. If you look in the picture, we designed a custom PCB for about all of our toy, just to make sure that it's well suited for the size of the toy and also for the feature set of the toy. So you can have custom shapes, you can have custom size, the color of your choice on the PCB, and you can also add your company logo, so it makes something very professional. At the same time, most of the wires from your prototype will become PCB trace, so that's a lot less failures. Imagine you make a prototype and you want to show that to one of your customers. When you move the prototype, there's a big chance that one of the wire will disconnect and your demonstration will fail. So with the PCB, it's a lot less wires. We added 2 resources that we recommend if you want to learn how to make PCB. Those are good. This way, you can go from the burger Arduino design, and if you look in the picture on the right, that's the custom PCB we designed for the car. So as you can see, it's very easy to fit inside the car. At the same time, when you make your PCB, you will also be able to make your dev board, which is the perfect development kit for you. You can make it compact with all the pins that you need exposed. You can add a voltage regulator section, so this way you can add any power source at the input and it will work well. You can add tons of LED, very useful for debugging. And if you usually use some sensors in your project, that's good to also have the PCB trace there. So for example, in our case, we use an accelerometer and gyroscope in most of our project. So we made sure that we can have the sensor if we require for a new idea. If you decide to make your PCB, you will need to make them. One of the choice is to make them yourself. So using chemicals and a printer, laser printer, you'll be able to create them, but what will happen is probably you're going to burn your hands and you will die. If you look at the picture on the right, the end result is not very interesting in most cases, and it's very time-consuming. So what we recommend is you go to a professional fabrication house. There's DF Robot, which is in Shenzhen, China. We really recommend this manufacturer. Osh Park ecosystem is very interesting too. What they do is they merge all the design from different customers. They put it inside a large board, they print the board, and then they split the design back and send every orders to everyone. So it makes very inexpensive boards. If you're lucky enough, you will have a fabrication lab in your city, and some of them can also make PCB. So it's about $1 per PCB in small batch, so very not expensive. Local business is very fast, but for prototype, their price becomes expensive very quickly. So now you have the PCB and the components, and you will need to solder the components on the PCB. A lot of people think it's very hard to solder those small, tiny surface mount components on a PCB, but it's not. If you have a good soldering station, brands such as Pace or Hackle, if you have a multimeter, clips to hold your PCB, you're good to go. If your eyes are broken, like my partner GP, you might need a microscope. Some components require a reflow oven. It's not that expensive, but if you don't have one, you can also use breakout boards, which are PCB with the surface mount components, which is already soldered to. And breakout boards are very easy to solder to your main PCB. So you have the PCB ready. What remains is to write the code that will work on the microcontroller. Depending on the microcontroller you choose, most of the time it's simply to go to the manufacturer website, and they offer the tools so you can write your C code, or if you're working with very low cost microcontroller, it can be in assembly language, and this way you can program the chip. What you need to remember is there's a lot of existing code that covers about any sensors. If you look in the Arduino libraries or in their forums, if you also can watch the Embed platform, they have a lot of templates that works in multiple scenarios. So writing code for firmware in electronics is about the same as writing code for low level on a PC. The biggest difference is at the end, you will need to put the code on a physical object. So if we take a racer example, at the end, I was ready with the toy itself. JP gave me his code that I put inside the microcontroller, and then I used glue, closed the car, and then started to play on the iPad. But because his firmware was full of bugs, I play on the iPad, and it didn't work very well. So I had to find a way to remove all that glue. And solder cables is very easy to break something and put a new software inside. So it doesn't make a lot of sense for a toy. What we suggest is you start from the beginning with firmware over the air. And it's not very hard because manufacturers now help you to do that. Nordic, for example, they have an Android application that you simply have to go to their firmware menu. You select the firmware from your Google Drive or Dropbox account that you push from your PC, and you pair it with your Bluetooth toy. And a minute later, you have the new code running on the electronics, and you didn't have to open anything. So you won't break something. So that's it. You have your electronic, and you need a video game software that will connect. And for us, the best engine for that is Unreal. So you have iterative.
Simon, give me that. Always use Unity. Much easier. As you guys know, iterative, very easy for iteration, build and run again. It's very practical. Most of our tools are working under Windows, and so as Unity, so it's great. And before working for prototyping under Unity, we've done a lot of work on different kind of engine with Visual Studio, and now with the integration they've done for Unity, it's wonderful. It's working great. And C#, obviously, very fast and efficient. We can find tons of code online, so it's easy to reduce time of programming something. We can always find a bit of code online. Then we use a lot of native extension for all of the communication layer. So we need to talk with the toy, so there's some kind of native code to do for each platform for the communication. And then for the interface, we use Uniswift because of the most of the workforce at Frima has a huge background using Flash, and so it's very easy to just create interface with Flash and export that and just run it using Uniswift, a plugin like Uniswift. And the final, but I think the most important one is it really requires only one person to do a small prototype. And this is something we greatly appreciate because we're trying to stay as lean as possible while prototyping. And this is a great thing about Unity. It's easy to work in a small team. So when we have the core of the game ready, we need to communicate with the toy. We have a couple of options here. The first one would be RFID or NFC, and I'm sure that many of you here have an Android device supporting it, but sadly, most iOS devices don't. And we wanted to have our toys running on every platform, so that wasn't a good pick for us. Then there is audio recognition or audio signal. It's a very cheap option, very low cost, but there's no multiplayer possibilities and very low reliability. And then there is wired communication, so USB, HID, or UART. Both protocol works great, very reliable, everything is good, but when you want to do a prototype like the cars, where you move around, not ideal to have that big wire behind your toys. And then there's the much more logical wireless communication. The first one to think is Wi-Fi, but for toys with the kids and authentication protocol, plus it takes a lot of energy to make it run. We thought that wasn't a good pick for us. Then there's Bluetooth, and again, a bit like Wi-Fi, the pairing kind of messy, and depending on what you do, it can take more energy. And finally, there's Bluetooth Low Energy, which is the big winner here. All the prototypes we are making use that. As the name says, it's not taking much energy, and it's ideal to run on batteries. And there's no real need for pairing or association, so we can just stream data depending on the project, but we can just stream data and interpret that directly in any device. So Bluetooth, the winner. When you start sending data from the toys to your game, you may receive a lot of data. If you think about the car, accelerometer, gyro, quaternion, all stream at hundreds of frames per second. Not ideal if you want to trace that in a Unity console. So you need better tool than that to interpret what's going on. And for this, we used a BLE sniffer hardware. You can buy that directly online, or it may be embedded into your development kit. So like us, we use the Nordic chip. It's already inside of the development kit, so it's very easy to use. Then we wrote a C# communication bridge, basically take anything going from the BLE sniffer and redirect that using a local TCP server to Unity. So we can see inside of the Unity editor any move we do with the car, for example. And at the same time, on the other side, it's sending the same data to a plugin called SciShart. And this plugin is made to display any kind of hundreds of type of graph. And it's very, very optimized, so it can handle millions of points per second. So you can take a look at the real case scenario here. We have the car. You're just following the orientation on the iPad, or it can be on Unity editor directly. And at the same time, you have a graph of any kind of move, each axis, what's going on, zoom in, zoom out, and really track what's going on. OK, and so we have the toy, we have the electronics, the communication, the Unity core. But what we don't have yet is a toy. And when programmers start to making toy, they need new tools. So what we've got here is a 3D printer and CNC router. Those two are pretty much a must. The difference between the two is the 3D printer is creating an object by stacking up layers of plastic, whereas CNC router is taking a raw block of material and remove layer by layer content using some kind of drill or router. Depending on the project you do, you might also need molds or rubber parts. You can use silicone or urethane rubber for that. And then if you want to do some kind of visual design over the toy, some spray paint or airbrush is great. Then when your toy is made, but you need some kind of rework or small modification, a rotary tool and all of the subtool like a Dremel is very, very practical. And when you don't know what you are going to work on next, a generic toolbox. So a lot of different kind of tools. And I don't know if there is any maker here, but they surely know a lot of duct tape and hot glue is a must. So hopefully, when you use 3D printer and a CNC router, you need new software also. So you cannot use classical 3D design software. You need to use CAD 3D design software. And the difference between the two is basically you have parametric design. Everything is driven from the dimension. And so it's very precise and can be spliced up for your 3D printer or CNC router. There are open source or free solution for that. I'm used to work with Autodesk Inventor, which has worked great. I've been using that for years. And now there's even a plugin called HSM that is made to handle CNC type of machine. So it's taking all the cut and different things you do on your object and convert that to G-code, which is then interpreted by your CNC router. So hopefully, when you have your physical toy and have embedded the electronics and the communication running and the gaming running, you have a new smart toy that hopefully kids will love to play with. So this is pretty much all, but remember, take the time to pick the right components. It's very important. Watch out for the Burgardino monsters, and assume Simons make a lot of error. So firmware over the air is a must. Use Unity, not other things, and make it beautiful but robust. And this one we learned the hard way. When we first showed the workbench to one of the vendors at Frima, he took the hammer and smashed the thing over and over again so hard, it just broke everything inside. He broke the sensor, and nothing was working, so make it robust, you never know. And debug and iterate, it's like the software, classical software, same goes with smart toys, and yes, things can catch on fire. So thank you.
Any question?
Any question?
Okay, so I don't mean to date myself, but the last time I did circuit board design was in the early 1990s. And the tools obviously have moved on a lot, and I couldn't believe the prices you were talking about for getting prototype boards, because in my day, it was $750 to get one prototype board done. So what do you use for your circuit trace layout software that supports multi-layer boards, and are there good alternatives available in either the open source community or at least in a non-Windows platform these days?
I would say we are on the Windows platform mainly. So the solution we use works on, I think it works on other platforms, but mainly on Windows. So Eagle was there in the day, so maybe you try that. We started with Eagle, which is, I think, probably a very good solution if you want to invest. It's low cost, but still do everything. And then we switched to Altium Designer lately, just to make sure that when we start prototyping for manufacturer, other vendors, they already have designs sometimes that we need to import. So in our case, we had to have those two software. Yeah, so I don't know, it answers your question?
Well, the question also about the price, with the China, China production, like DF Robot, to produce the PCB, it's very, very cheap. We said, around $1 per piece. It's often in batch of 10 boards, and it's, yeah.
The only difference is they're going to make the PCB itself, but they won't assemble it for that price. So assembly is still high cost, but if you, like we said, you can do it at home now with the right equipment, those are not very expensive too. You will have the PCB for about, I would say $10 for 10 piece, 5 centimeter by 5 centimeter, and then you can expand, the price will go along.
And one tip for anybody here who is learning to solder for the first time, he's right, it isn't that hard, but the thing you've got to remember is heat the piece, not the solder directly. Heat the item you're going to solder to, preferably the board. Let the heat from the item transfer to the solder wick, not the other way around.
You're right for that.
Thank you.
Thank you.
Have you guys ever experimented with Squink or any of the other electronic 3D prototyping tools that are out there? Like they're kind of like 3D printers, but they're pick and place and that sort of thing?
Well, we work with what we have. We don't have this kind of machinery, so no, we didn't really work with these. But yeah, I'm sure it would be interesting to try it out.
Hi, I have a question more about kind of the object design of these smart toy controllers and just sort of like what kind of things you consider, because I mean obviously there's things like the age appropriateness of the workbench and it's non-choking, and like a die-cast car microcontroller is easier to bring around or distribute than its full-size equivalent, but I was just wondering what kind of other things you considered when you were designing these controllers.
Well, in one of the first line we were talking about Brainstorm, and in different Brainstorm we had, it's not so much about specifics. We're just trying to see what would be a good place to be and what kind of toy would be a great pick, but there's no main direction in this way. So we showed you 2 prototypes, but we've got multiple others, so it's not, yeah, we don't have that main direction to follow.
Thank you.
Thanks. All right.
Anything else? Well, thank you.
Thank you.